This is a extended version of a presentation made a few days ago at the United Nations Oceans Conference. It was the first meeting of all the nations of the world, or most of them at any rate, to discuss oceans issues. And it's just a historic meeting, and this is the United Nations statement on what came out of it. And essentially, countries agreed that the oceans are in deep trouble for a lot of reasons, and they list the different causes, and they go through making some sort of commitment to try to make things better. And that involves two things. One is trying to slow down the rate at which the oceans are dying, slow down the pace at which we're seeing the collapse of ecosystems worldwide and fisheries. But also for the first time, and this is what's really important here, it mentions regeneration of ecosystems in order to restore their economic and ecological services that are being lost. So that's completely new here. That's never been mentioned in any United Nations conference on climate or oceans before. So that is new. That's only 1% of the total. 99% of the focus of this meeting is essentially on trying to control overfishing, by using higher technology to find and catch the people responsible, or to protect larger and larger areas. The problem is that won't restore the fisheries in areas where the ecosystems have collapsed and are no longer providing either shelter or food for the fish. You can protect those all you want and the fish won't come back. So without active restoration, and that's the point of our presentation, we won't be able to reverse that. And that's reflected here in this document, along with a lot of commitments to try to end plastics in the ocean and other things. It's really in many ways an excellent document. It's vague, as UN documents are, and that it doesn't really give specifics as how this is to be accomplished, but it basically expresses for the first time on a global scale a commitment of governments to try to do something to stop the rate at which we're throwing our garbage and plastics into the ocean, doing something to recycle those on land and help restore marine ecosystems. So it's a very important first step, even though the guidelines of how to do that are not made clear. And this is what the point of my talk is going to be. So this is, we will provide links to the Ocean Conference. The particular event at which I spoke, let me give some background actually about these United Nations conferences. There are hundreds of what are called side events that are being presented in which specific topics are being discussed. Fundamentally, each side event is organized by some government or some international funding agency in order to basically highlight what they're doing, in order to try to get publicity for what they're claimed to have accomplished, in order to get more money to do more of the same. And so each one of these side events reflects some sort of interest group within the system that has spent a lot of money, and in part on promoting these sorts of side events. It's an odd mixture, and as you'll see, almost all of them are groups that are focused on a top-down command and control view of ocean resources. There are very few exceptions, and I'll discuss that a little bit as we go through. This particular side event here was entitled Energy Services from Organic Waste, Integrated Waste Management Solutions for Coastal, Marine, and Freshwater Protection in Small Island Developing States. And in other words, it's designed to see how island nations can recycle their waste to provide energy that otherwise they'd have to import at very high expense, and to be more efficient, because most small islands spend up to half of their foreign exchange earnings importing fossil fuels at extremely high cost, and the energy prices for the consumer are very, very high in these island nations. So it's an issue. So this is basically focused in part on energy recycling, but also on nutrient recycling, because the other component of organic waste, they've been promoting programs to basically turn compost into energy, or garbage into energy. But what we're trying to do here is also to recycle the organic waste to prevent the nutrients from contaminating the ocean. That's why I was asked to speak, because that's something I've done a lot of work on in the Caribbean and other places. And it was organized by the Caribbean Center for Renewable Energy and Energy Efficiency, which is it's a Caribbean-wide program related to the Caribbean Community Center for Climate Change, which is an intergovernmental organization representing almost all the Caribbean countries. And it was co-organized by SIDS-DOCK. That's a small island developing states network of information transfer that had been set up by Dr. Al Binger at the Caribbean Community Center for Climate Change. He's also the head of the Secretary General of the Center for Renewable Energy and Energy Efficiency. So it was also organized by the United Nations Industrial Development Organization, which is a major UN organization focused on basically promoting energy. It's centered in Vienna. And by the Caribbean Community Energy Program, the Caribbean Community is essentially an intergovernmental network of almost all the Caribbean countries. The Caribbean Community Climate Change Center, which again is an intergovernmental organization representing most of the Caribbean countries. The South Pacific Regional Environment Program, and that is a network of pretty much all the Pacific countries dealing with environmental issues. So they're all members of that. And then supported by the government of Austria and the government of Spain. So these are the people who had promoted that. And I was asked to talk about solutions to restoring the marine environment, in particular how to reduce the impacts of waste from land. And I'm going to now show you the PowerPoint presentation made there. It's entitled New Methods for Large-Scale Restoration of Marine Ecological and Economic Services in Small Island Developing States. And in fact, the applications are much more broadly applicable. They're applicable in all ecosystems, as you will see. Now, nearly 60% of all global economic losses from the deterioration of ecosystems worldwide were estimated over about a 15-year period about 5 years ago by Robert Costanza, one of the world's top ecological economists. And what he found was that in all the worldwide losses of money that people could earn from what ecosystems were doing for them, about 60% of all those losses were due to the deterioration of coral reefs alone. Now, coral reefs only occupy 1/10% of the Earth's surface, so we're seeing a rate of loss of economic services at 600 times the global average in coral reef environments, and that is mostly being borne by the small island states and the island nations. And they are the first and worst victims because we've already lost most of our coral reefs to high temperatures. So it's a very serious problem. I will come back to that a little later. Now, for sustainable development of small island states, I just want to make 3 points very, very quickly, and that is, one, the problem is far worse than anyone imagines. And the reason for that is very simple. It takes 1,600 years for the deep ocean to turn over and mix. The bottom water is at refrigerator temperatures, 4 degrees C, just above freezing. Until that warms up, we will not feel the full effect of temperature warming at the surface because that heat is warming up the deep water. That holds 95% of the heat capacity. So when we increase CO2 in the atmosphere, it's going to take thousands of years before we feel the full temperature effect. We haven't felt it yet. The Intergovernmental Panel on Climate Change projections are for 5, 10, 20, 100 years. The response takes thousands of years, therefore the IPCC projections are missing more than 90% of the actual response. They're just getting the very first part. The IPCC projections were based on a time horizon that was a political mandate. It was not a scientific mandate. So it's very important to understand what we're really headed for is far worse than they say in the long run. We cannot prevent that problem simply by emissions reductions. We have to get rid of the dangerous excess CO2 in the atmosphere by storing that back in the biosphere and the soil where it came from. And if we do that, we can solve the problem. So the methods to do that are mature. They've been developed. We know how to solve these problems, but the solutions are simply not being used on the scale that are needed. And the window of opportunity in order to use these solutions effectively is very narrow and it's rapidly diminishing. So therefore, immediate action and not talk is needed. And I will show you some of these solutions related to the oceans and small island states. But first let me say, we've lost most of our coral reefs. They're the most temperature-sensitive ecosystem of all. They're the most pollution-sensitive ecosystem of all. They need the cleanest, clearest, purest waters in order to survive. And we understood their temperature limits 30 years ago in 1987 in Jamaica, which is where coral reef research was developed. We first saw high temperature bleaching in 1987, and we were shocked. We were shocked that such a little change in temperature 30 years ago could have caused our corals to turn white and to completely stop growing, and a little bit more to kill them. We were astonished, and we warned people at that point that temperature was the cause. We developed the methods for predicting coral bleaching accurately from satellite data nearly 30 years ago, But governments didn't want to act because they did not want to deal with fundamental causes. They were in denial of the known facts that coral reefs could not take any higher temperature already at that point. And since then it's got progressively worse and worse, and we've now lost most of the corals due to heat shock from global warming. The result of that is what reefs we have left are standing dead. They're isolated corals here and there, and they're not serving, they're not able to serve the biodiversity, the shore protection, the fisheries, the ecological and economic services they used to provide. They're barely functioning anymore. And simply protecting dead or dying reefs is not going to bring them back if we don't solve the root causes and we don't restore them actively. So, it's a very serious matter, and we need to start moving ahead on this very quickly. This is the first high-quality underwater photograph of a coral reef from 1948. We're losing their beauty too, as all these corals vanish. I'm going to be very quickly talking about 13 practical solutions to some of these problems, and I call them SID technologies because these have been developed and applied in small island developing states. And we'll go through them very quickly. The key point about them is they're available and they're not being used at all at the scale that is being needed. Of these 13 technologies, only the first is a land technology. All the rest are marine technologies, and all of these, except for the last, were invented and developed in small island developing states with no outside funding or help or assistance. We're ready to share these small island developing states' technologies with the rich countries to help them solve their environmental problems too, through environmental technology transfer, even though we never received any help at all from them. The first one is cleaning up polluted coastal waters. Just like we're throwing away the energy content in our garbage and not recovering that and recycling that and avoiding expensive energy imports, we're throwing away the nutrient content in our waste as well. And the result of that is we're polluting the marine environment. Every coastal area, reefs in the world around populated areas are being smothered by algae because of the nutrients coming in because we don't treat our sewage and agricultural waste properly. That causes algae to proliferate and kill the reef. There's only one place in the world where those weedy algae have ever been gotten rid of long term, and that's what I want to show you. And that's a bay in Jamaica that we cleaned up permanently by recycling all of the land-based sources of nutrients on land and preventing them getting into the ocean. Once we did that, the algae simply began to die back, turn pale and die back within weeks. And within a month, 2 months, they were gone completely and the reef recovered. So it's amazingly fast and effective to do, but you have to control all the nutrients that are entering that area. So you need integrated management of the entire watershed in the coastal zone, and you need to recycle these nutrients as close as you can. The key thing to understand is the land is starved of nutrients and the oceans have too much. We're washing our nutrients off the land into the ocean, and we have to import very expensive fertilizer to keep the productivity going. Once those nutrients are in the sea and are contaminated with salt and diluted, we can't give them back to the plants. We need to recycle that in fresh water as soon as we can. This is what we did in Jamaica. We found a bay. One side of the bay, the reef was overgrown with green algae because of the phosphate coming from the laundry detergents. The other side of the bay, the reef was overgrown with red algae because of the sewage effluents that they sterilized with chlorine, and then they dumped it right out into the water in front of their beach. So red algae were proliferating. And I went to the hotel and I said, it's very easy to clean this up. All you have to do is take your laundry effluents, instead of dumping them into the water, put them into the sewer plant. Take your sewer plant over effluents, instead of putting them into the sea, pump them up the hill, use them to water the plants and the trees and the ornamental lily ponds, and so those plants will suck up those nutrients, grow faster, greener, you'll have more flowers, and there'll be no nutrients by the time that water reaches the sea. When they did that, as I say, within months all the weedy algae were gone, the corals came back. So that's the only place in the world that's ever been done. And this is the bay here in Jamaica where that was done. This side of the bay was green, this side was red, we cleaned it up. And the same principles can be applied everywhere, but of course, it's much harder where there's more than one polluter. At any rate, the methods exist to do that. We need to be applying that in a long scale, because that way we'll enrich both the land and the sea and the economic services we get from both. So it's an essential strategy for the future. Now I want to talk about what we do once we clean up the coastal waters. First of all, we need to restore coral reefs. We've developed a technology called BIOROCK electric reef restoration. This was invented in Jamaica in 1987, 30 years ago, the same year that the mass high-temperature coral bleaching hit us for the first time. And we've done projects, more than 400 projects in around 40 countries since then. Almost all of them small island developing states or island nations of one form or another. And what our technology does is it uses a trickle charge of electricity. We greatly increase the settlement, the growth, the survival, and the resistance to environmental stress, including high temperature and pollution, of all marine organisms. So we're able to keep reefs alive where and when they would die from severe environmental stress like high temperature bleaching, and we're able to grow them back very quickly in places where there's no natural recovery. In fact, it's the only method we know that protects corals from high temperature. It also works in cold waters. There we grow oyster and mussel reefs, so it works in any ecosystem. We grow back very complex ecosystems rapidly. And here's an example of what we did in Bali. And this is an area, when we began, the reef was dead. There was about 1% live coral cover. That's the same area 10 years later, completely covered with corals. It spontaneously settled and grew at incredible rates. And we've done this again over and over again, and we can do that with any marine ecosystem. In doing so, we restore fisheries habitat because these reefs create the shelter and grow the food that provides complex ecosystems. Marine protected areas simply don't work if they don't have the shelter and food. In a reef, we'll see one hole that a lobster can live in, one for an octopus, and that limits the population. We can actually build BIOROCK reefs in any size or shape. We can make them specific for different species, but what we can do is we can have many layers of hiding places, and we can wind up with incredible densities of not only fish and shellfish. We can also make floating reefs. We can promote the growth of pelagic open ocean fish like tuna or mahi-mahi. So there are huge possibilities. Fishermen can use this technology to restore their fishes. And indeed, in Indonesia, we've done just that. We've taken fisheries that have collapsed. We've produced so many fish that has fed out to the surrounding areas that we've restored the fisheries, and the fishermen want everyone else to do the same. This is a 4-year-old BIOROCK reef in Pemutaran, Bali, and there was nothing there. It was dead coral, rubble, and sand. And as you can see, by growing the reef, we've created huge amounts of fish habitat. We can use this technology to produce sustainable mariculture because we can make the habitat in sizes and shapes that are specific. When we make lobster habitat, the lobsters crowd in. When we make oyster habitat or clam habitat, there's huge possibilities. And we don't need to feed them because we're growing a very complex ecosystem that's generating its own food. So they can be much more productive than natural reefs, and fishermen can produce much more in much smaller spaces. As a matter of fact, this is an example in Bali where we generated snapper populations. I'm very happy to say that today the Solomon Islands government has approved a plan to make the world's largest mariculture and hatchery operation in one of the world's largest and remote atolls using BIOROCK technology. This is Ontong Java Atoll in the Solomon Islands. It's one of the most pristine. It's suffering from global sea level rise. Their islands are washing away, and the plan is there for the community-based management, just as we did in Bali, to grow sea cucumbers and giant clams in a sustainable way on a large scale, and also to use our method to protect their shores, which we'll talk about later. So there are enormous mariculture potential, sustainable mariculture potentials. They're very different from the current paradigm of mariculture. We can use this technology also to restore salt marshes. Salt marshes are all now rapidly eroding from global sea level rise. They're critical fisheries and shore protection habitats. When we use our methods, we greatly increase their growth, especially low in the intertidal where they get washed away, where root growth is slow. We speed up the root growth so we can establish them out on the seaward edges now where they're washing away. We have a site in New York City at a Superfund toxic waste dump, one of the worst polluted sites in the U.S. There we're growing seagrass using BIOROCK technology and solar panels. And the seagrass we're growing, the bottom, there's so many mussels that have grown around them. The bottom is about 6 inches or 10 centimeters higher than the surrounding areas, because that's the sand's just being washed away by sea level rise. So we're protecting the shoreline, building these green infrastructures. So that will allow us to protect them. And here you can see for yourself, there's a solar panel in the background. This is the salt marsh that we've grown at this polluted site. Would not be there otherwise. New York City is in fact at this moment building a huge storm drain to dump polluted storm runoff right on top of the site that we've been restoring for 10 years. We've also restored oysters, but that's in the background there, again using solar panels for power. We can restore seagrasses using these methods. Seagrasses are critical fish habitat, lobster habitat, and they're being rapidly destroyed. We've lost about half of them worldwide. We've lost about half the salt marshes worldwide. We've lost about half the mangroves. They're the most threatened ecosystem of all after coral reefs. We're wiping them out. What we've found is that with BIOROCK methods, people try to plant them and they wash away before the roots can be established. If the water's polluted or muddy, they just can't grow. So most of those have been failures. Our methods greatly increase the root growth of seagrass beds. They increase the shrimp, the crabs, the clams, and the fish living among them. In fact, we get such prolific growth of roots, we're able to make seagrass attached to bare rock, something that no one had thought was possible before. Here's seagrass that we're growing in Indonesia, corals growing like mad, seagrass growing like mad. We've done that in Bahamas and Panama and many other places. And here is in the Mediterranean. Here we're actually growing seagrass on limestone rock without sediments where they couldn't normally grow. You see fish around it. Close up of the roots shows mussels and clams and prolific growth. The controls all died. This again was powered by solar panels. So we're able to expand seagrasses. We're able to restore mangroves with these methods as well. Again, most mangrove plantings are failures because they wash away before the roots can be established. We believe we'll greatly increase the root growth just as we do with seagrass and salt marsh. We're doing projects already in Panama. Mangroves are being destroyed worldwide. They're being turned into shrimp ponds. And we're preparing a project right now in Kalimantan or Indonesian Borneo in order to take large areas of mangrove that were clear cut for shrimp ponds and convert them, reforest them with mangroves and turn them into habitat for orangutans. So we're critical. Restoring mangroves is really critical. They're essential for shore protection. They're protection against tsunamis and for fisheries habitat. So once you restore them, you get huge benefits. Here's an example in Eritrea where mangroves were being grown. And in doing so, the community that was here did several things. This is an area that mangroves had never grown before. And in doing that, they restored their fisheries offshore that had collapsed because of the juvenile fish that live among the mangrove roots. They were able to provide honey because of the bees that live in the mangroves. That was something they didn't have before. The leaves they're able to feed to their goats and their camels. So now they actually have food for animals. They can produce more animals and they sell those to the Saudis during Ramadan. So they're able to make money as a result of these mangroves. So it has had a huge impact. Finally, we can use these technologies to increase carbon sequestration. Mangroves, salt marsh, and seagrass are the most carbon-rich soils of any ecosystem on the Earth. They occupy about 1% of the Earth's surface, but they have as much carbon in them as the entire, more than the atmosphere. We're destroying them and putting that CO2 into the atmosphere, but if we restore them on a large scale, we not only restore their economic services, it's the most cost-effective possible way of removing CO2 from the atmosphere in the smallest area with the greatest economic and ecological benefits because of the shore protection and fisheries habitat that we generate. So it's crucial to restore them, and we believe the BIOROCK methods are going to provide an important technique for expanding all of these critical ecosystems and withdrawing that dangerous excess of CO2 out of the atmosphere in time to prevent runaway sea level rise and all the other things and temperature rise that will otherwise happen. That's a critical thing that we need to be supporting. Here's a diagram of the global carbon cycle and soil organic carbon. About a quarter of that is in marine wetlands, mangroves, salt marshes, seagrass, more than is in the atmosphere. If we restore that, we'll help draw down the dangerous excess and prevent runaway climate change. It's a critical matter, and we have very little time to do so. We cannot otherwise turn the ocean into a carbon sink unless we turn it into a dead zone. If it's a dead zone, then it'll be a carbon sink, but it'll kill all the fish, it'll stink of rotting eggs. The solution is right at the shoreline, because the mangroves and seagrasses are in fact storing about half of all the carbon in the ocean in their soils. We need to protect corals against global warming. The BIOROCK technique, we get up to 5,000% higher survival of corals after bleaching than surrounding reefs. The differences are quite staggering. In Indonesia last year, we kept whole reefs alive and growing, where the reefs without power had almost complete mortality. The difference was staggering. And the reason for that is that the BIOROCK, the electrical field we generate, is simply stimulating the natural energy generating mechanisms of corals and all forms of marine life. It's the natural way they make energy is from little electrical gradients, between the outside and the inside of their cells. And we're stimulating that. We're making them more efficient, recycling that energy and not having to spend it maintaining that voltage gradient. We just happen to be trickle charging them in a way that stimulates in the most beneficial possible way. And that's why we're able to protect corals against bleaching where nobody else can. Here's an example in Thailand. This is a coral that we're growing on BIOROCK reef that's completely unbleached. That's the same coral 1 year before. But you see all the corals behind it, except for that one, bleached completely white. And they all died. But this coral survived and kept growing through the bleaching event. And that's what we had in Indonesia last year as well, and in the Maldives in 1998. We can also use this technology for growing beaches back faster than global sea level rise, and increasing storms can wash them away. Growing BIOROCK reefs, what we do is what a natural reef does, which is the most efficient possible way to absorb energy offshore and dissipate it, and grow a beach back naturally. And so what we do is we grow BIOROCK reefs in front of eroded beaches. In the Maldives and Indonesia, we completely grew back beaches that had washed away literally in months, while at the same time regenerating the fisheries and the ecotourism resources that these areas have lost. And with that, we can not only grow beaches back against sea level rise, we can even grow islands, because we can grow the material faster than sea level rise can at the present time. And this is far cheaper than seawalls, which don't work. In fact, seawalls inevitably collapse. They focus all the energy of the waves at one point, that washes all the sand away in front and then under, and then they collapse. They simply don't work. Until they last, they'll protect what's behind them, but eventually they go. What we do is much cheaper and much simpler and has far greater benefits. Here's an example in the Maldives. When we began, the beach had gone, the trees were falling to the sea. This building was about to collapse into the ocean, and they said they couldn't possibly rescue it. They were going to have to tear it down and move it inland. We grew back that beach in front of it. We grew back that beach. You will see that dark line in front is a reef that we grew, and that's a beach we restored, and the building we protected. And that's been stable for 20 years since then. This is an example in Indonesia, and this is a bit over a year and a half ago, and this is a building about to fall into the sea. There's steady erosion, there's a cliff, the beach had gone, trees collapsing into the water, and that's how it was in January of 2016, when we built small BIOROCK reefs in front, and this is 8 months later. At beach, that's the same building, and that's the same tree. And 80% of that growth took place in just 2 months. 80% of that growth took place in just 2 months, and the beach has continued to grow, even under weather conditions that would normally erode into storms coming straight in. At the same time, we've grown the reef and the seagrass and created fish habitat. This technology also acts to reverse ocean acidification on a local scale. We can grow oysters and corals in acidic water without any problems. For example, in a Superfund toxic waste dump site in New York City, the oysters we were growing with electricity grew much faster than those that didn't have it. And then in the winter, when the water got very cold and acidic, because CO2 dissolves in cold water, the BIOROCK oysters continued to grow and had bright and shiny shells and had 100% survival. The controls, 93% of them died, and the ones that survived, their shells were shrunken and dissolved and chalky and crumbling and falling apart. This shows here the growth rate of the oysters with the BIOROCK method, higher and lower levels versus the controls. And this shows how the controls, 93% of them died, how they shrank in size because their shells dissolved, whereas the ones we were powering all survived and they continue to grow all winter with shiny shells. So we're able to deal with ocean acidification, the effects on mariculture. We produce building materials from the sea. We're growing solid limestone rock that's 3 times harder than concrete. We can do it in any size or shape in the ocean. Structures we build are the only marine construction material that get stronger with age and are self-repairing. They actually grow, damaged areas actually grow back first. Now with that, we can grow construction material in islands in almost all cases at much lower cost than importing concrete. It produces a harder material or much more permanent material. In addition, we can actually grow cements in the ocean that absorb CO2 from the atmosphere when they set, that are even harder than this material or ordinary concrete. And we believe this can be produced locally at a much lower cost, or significantly lower cost than imported cements. Furthermore, but the key is developing the renewable energy resources, and that's the last of these 13 technologies, and the only one that wasn't developed primarily in small island developing states. We've done this with partners in the rich countries abroad. Oh, sorry, this is the material we grow. This is from the Maldives. This is 2 years of growth. Material 3 times harder than concrete, growing around steel bars, which we completely prevent the rusting and corrosion of. This one here is a piece from Louisiana. It was completely covered with oysters that grew to adult size in months. But finally, we need to develop ocean energy. The process we do uses, we use the power of the sun with solar panels, windmills, we use tidal current generators, and we use wave energy generators. So we can use any form of sustainable energy, and our goal is, in particular, to develop ocean energy. That's essentially, that is completely untapped in developing countries, in fact anywhere in the world. It is our largest renewable energy resource, in particular for island nations. So we have been working, collaborating with many of the world's top wave and tidal energy devices, and they've been giving us their prototypes to test in order to try to grow shore protection reefs to protect atoll islands from washing away from global sea level rise. And then once we tap that, well, then we can do a great deal. This is a wave energy generator that we use at our projects in Indonesia. It's a float that moves up and down with the waves. Every time it moves, a permanent magnet generator makes a little bit of electricity. We can make up to 10 kilowatts of energy in about a 2 square meter float with something like that, in a wave about 1 meter high. With these you can tap small waves like that, so you can make energy almost all the time on most marine coasts. So there's tremendous potential with that technology once it's developed. It's a technology that uses the movement of the surface. Very simple device. This is a device designed for us that uses bottom surge. It's a very different device. It's mounted on the bottom, and it's a scoop that moves back and forward as the wave surge goes up and down. And that generates, again, power. It's mounted at the bottom and it generates power at the bottom. But that's able to make even larger amounts of power because they're using the movement and the momentum of the entire water mass to generate energy. And with those, we think we can basically grow back reefs and save atoll islands from disappearing. So that's huge potential. But none of this, in my view, is going to work if we don't do it through bottom-up community-based management. All projects need to be maintained, that's a fact, and we work directly with the communities that are living there. They're going to be there all the time. They're the ones who need to learn how to manage their resources sustainably for their future. It's their future that we're talking about, and they want to do that. They want to be more productive and less destructive if they knew how. But when we see top-down management, it all fails the second the money dries up. The command and control top-down method simply has not worked. It simply has not worked at all. And unfortunately, 99% of the UN Oceans Conference is about top-down command and control measures. Finding illegal fishermen, capturing illegal fishermen, expanding the areas where they can't fish. Only 1% of this is about regenerative development. And that is the critical thing, is to make communities regenerate their resources. At the same evening that I made this presentation, my Indonesian group, Yayasan Karang Lestari, or the Indonesian Protected Coral Foundation, received the highest honors. They were the guest of honor at the World Ocean Day celebration at the United Nations Oceans Conference, organized by the United Nations Development Program, the government of Germany, and many others. Unfortunately, I don't have that in front of me here, so I can't list all the sponsors. There's a meeting of people from 150 countries, And my group was honored for the following reason. They had turned a reef that had been destroyed, that had destroyed their fishes, destroyed their tourism. They grew that reef back. And in turning economic disaster into economic opportunity, they've gone from being the poorest village on the island of Bali to being one of the most prosperous because of the people who come from all over the world to see those reefs and swim in those huge schools of fish. So they've restored their environment, they've restored their fish, and they want all the other fishing villages in Indonesia to do that too. And for that reason, our team won the United Nations Equator Award for Community-Based Management, and we also were awarded the Special UNDP Program, UNDP Award for Oceans and Coastal Management in 2012 in Rio de Janeiro at the Earth Summit. And my Indonesian team was especially honored at the United Nations the same night I presented this presentation for that work. And we hope to see that happening worldwide with fishing communities. Here's an example of what we do. I did last year in Vanuatu, and this is where I'm working here with a fishing community. Their coral reef was destroyed in 1943. All of a sudden, one day, 150,000 people from abroad showed up, dredged their reef up, turned it into an airport, and then they all left 6 months later. The reef never recovered. And what we're doing with this community here is growing back that reef, and here you see we're learning how to build the structures. Here we're attaching corals to it. And especially, we're training the next generation. The kids love this. This is their future. To restore their reefs and generate their fisheries and a lot of opportunities. They're so eager to do it. And that's where we have to go. We can't wait any longer for those people who can't understand or won't learn to do the right thing. We've got to start doing the right thing every place we can to regenerate our ecosystems everywhere we can in order to prevent runaway climate change. Regenerative development to reverse climate change is the key. And we have the tools to do so, but we have very little time to implement them. We've talked and talked for decade after decade at these meetings. We need action now. Thank you.